different style. Yeah, so we're going to talk about reactive streams today, which is something that, so I'm Jordan Parmer and I'm a software engineer at Osberg, and we use reactive streams in our workflow, and that has solved a lot of the problems for us, and so we've been using it for a couple of years now, so I thought it was time to give a talk about it. How many of you have worked with reactive streams before? Is this going to be new for everybody? Okay, cool. How many of you, let me see what we got here. Yeah. How many of you work in data processing workflows? Okay. How many of you stream a lot of data from like a web application? A few more of you. Okay. What about reading data from files or databases? Okay. Eventually I get everybody, because this applies to all of those sort of things. And so what is reactive streaming? So reactive streaming is a common mechanism to move data across an asynchronous boundary without losses, buffering, or resource exhaustion. So in a nutshell, what we're trying to solve with reactive streaming is the problem of streaming large volumes of data. It might be an infinite amount of data. There may not be any deterministic cap to it. It's not finite. And trying to do that in such a way where all pieces of your pipeline handle resource management, back pressure, you can do things asynchronously. Those are all problems you run into when you're trying to stream large data sets. And typically what's been done in the past is you'll end up kind of writing your own tools to implement this. So let's say, for instance, you're going to pass data to a web service somewhere. So you've loaded a bunch of data from a file, and you need to submit that to a web service. All right. So the first thing you're going to do is, you're going to load in all the bytes of that file, and then you got memory that's growing in response to that. You're going to generate requests to a web service, and that web service may or may not be able to handle all of the requests that you send it in a timely manner. And eventually, the web service itself might return an error saying, hey, I can't handle any more requests. All the threads are taken up. And then you have to deal with like throttling at some point. So you're going to have to implement that on your side, and you're going to put a lot of logic there. And after a while, it just becomes a pretty complicated problem, which was originally very simple. So reactive streams is it's not a single technology, it's a spec that came out that different technologies can implement to solve some of these problems. So some of the common use cases, it's really ideal for data pipelines. So if you do a lot of like ETL work, or you're processing large volumes of data, your Twitter, you're sucking in tweets, your Facebook, you're pulling in posts, it's really great for that kind of thing. Unbounded data volumes. Message queues, so if you work with any kind of like, message brokering system, it's great for that, for streaming data. Streaming from network sockets, files, even iterators. If you work, like for instance, in JavaScript, they got the whole RX ecosystem, and a lot of that is taking event-based data and streaming it. And it's a very similar paradigm. Those kind of borrowed from each other. So you can take something as simple as just a basic array processing and use reactive streams to do it. And you'll see the advantages and why you might want to here in a little bit. So at a very high level here, I just want to kind of throw out some diagrams before I dive into the specifics. But at a very high level, what we're doing is we've got a data source on the left, and we got it emitting elements. Now those could be any kinds of things. It could be bytes, it could be like lines from a file, it could be actual records in your code base. It could be any number of things. So you're going to tell it how you're going to partition the data coming in, and that's very simple to do. You're going to run that through a series of transformations, and then you're going to fold those results into some kind of result set at the end. So being in functional programming, we're familiar with kind of the trinity of filter, map, and fold. And that's present here. That's exactly what we're doing. And you might want to do some elaborate workflows. You might want to break your path up. So you might want data to kind of split off and fork and then all those merge back together based on certain conditions. And you might even want to distribute that. So you might want some of those paths to either, to cross some sort of asynchronous boundary, whether that be threads, actors, or processes, maybe even machines. So some of you might be wondering, why are we talking about this at a functional programming user group? And it's because a lot of this borrows from the functional programming paradigm. The reason this is possible is because we're looking at data in a way that supports composability. It's lazy. We're going to look at it in an immutable way. And then from that, we get the benefits of being able to distribute and parallelize our workflows. So a lot of the theory that you get and the benefits you get from functional programming are going to be applied here. And so everything we're doing follows all of the FP tenets. In fact, whenever you look at the actual code here in a minute, it's not going to look a whole lot different than what you might already do in a functional programming language. And so that's a very nice benefit, is that you can adapt this without changing a whole lot. Now, the React word is very overloaded, so I want to be crystal clear in what we're talking about today. Because if you're in the JavaScript ecosystem, people love talking about React, and there's two different flavors of React, depending on what you're talking about. So we're not talking about React.js. But we are talking some of the React programming from the JavaScript RX libraries kind of overlap here. We're also not talking about reactive systems. So let me explain what I mean by that. There is, a couple years ago, a company called TypeSafe and Lightbend came out with what was called the Reactive Manifesto. Has anybody heard of that? A few people? Okay. So the Reactive Manifesto, let me see if I think I got a tab here with that. Yeah, here we go. The idea here is that we are going to build systems that have 4 tenets. It's going to be a message-driven system that is going to be elastic, responsive, and resilient. And there's different criteria for what each of those means, but essentially, elasticity allows us to automatically scale to, based on our load demands. Responsive means that we have high availability in our systems, and then resilience means that if there's an error or something happens, that we still are up, and we can handle that error well. This is reactive systems. We're not really talking about this today, so don't get confused with what this is. What we're talking about is reactive programming. So on the left, you have reactive programming, and this is a very application-centric view. So we're talking about down at a process level, how we're going to handle streaming information coming in. A reactive system is more of the systems-wide process interaction view. So it's a slightly different problem. Okay, so just want to be clear there. A lot of people, when they start researching it, start researching reactive systems and realize that we're somewhere totally else. Okay, so the reactive streams is a spec. It's not an actual library or thing. It describes an interface for how to do the streaming here. Now there are different, depending on what tech stack you're on, there are different implementations of that spec. So today, because I'm very familiar with Scala, as some of you know, I'm going to show you akka-streams, which is the akka implementation of the Reactive Streams library. But none of that is specific to Scala. So this works on the JVM, it works in Java. But if you go over and use some other framework's implementation of it, all of the concepts are still going to apply. So all the terminology we use and the things that are covered are still there. So here's the general workflow. We've got a source or a publisher, depending on what they call it, and this is going to emit event data. And it's going to be immutable event data. So if you're familiar with like event sourcing, where you have an event that represents a certain particular state and time, we're not going to change that. It's just this is what this object represents, and it's going to flow over to a sink or a subscriber. And that's going to consume and do something with the data. the source can be anything. It can be a file, a network socket, it could be just an array that we have in memory. It can really be anything. It's abstracted out what that is. And there's all kinds of ways to hook into different sources. And then we're going to have a series of chained operations that we will apply to the data. So if we're going to create a pipeline, and through the pipeline, we'll apply different transformations until we get to the very end where we have our results there. Okay, now this is the ideal when we're talking about streaming data. Ideally, our publisher and our subscriber are in sync with demand. So it's great if the thing that's subscribing or listening or consuming the data can match the computational time as the publisher, or do better. So if my subscriber can, as fast as I get data, I can handle that data, that is ideal, right? But unfortunately, that's not really how it works most of the time, okay? What we typically have is a fast publisher and a slow subscriber. That means that the publisher can produce data faster than a consumer can deal with it, and that's what we run into a lot of our problems that we have to program against, okay? So in a push-based system, so that means the publisher will push data downstream. Let's say that in this case, we can do that at 1,000 operations a second, and we've got a subscriber that can only do or handle 10 operations a second, okay? Now we're going to run into problems pretty quick because we have to decide what do we do when we can, when the consumer can no longer handle that load. So we either have to set up like a buffer or throttle the stream somehow. We might run out of memory depending on what we do there. So here's a picture where we're showing a buffer. So let's say we've created a buffer. We could say, okay, we can hold up to 4 elements in the buffer while we wait on the subscriber to finish its processing. So what do we do once the buffer overflows? We could drop them. All right, just throw them out and say, well, the buffer size is the buffer size. We could somehow communicate upstream that, I'll get to you later, resend them. All right, but that's kind of complicated to handle. We could extend the buffer and say, well, we're going to have a small buffer, and then as we need to, we'll increase it and try to allocate more memory. But then eventually we're going to run out of memory, and we still have the same problem. All right, so it's a push-based architecture is pretty hard to deal with. So the idea with the reactive system is that we're going to have reactive with back pressure. And back pressure is really key to this technology. So what back pressure does is it inverts the demand flow. So instead of something pushing downstream, your consumer will signal demand upstream and say, right now I can handle this amount of data, so go ahead and send this to me. And then the publisher's got to kind of wait before submitting anything else. So the subscriber says, okay, I'm going to send out a request or signal upstream, and that creates what we call demand. And then we respond with more records based on that demand. So in this case, if we have a buffer of size 4, and we've got 2 open slots, then we can submit a signal for 2 more, and the publisher can satisfy that. All right, so let's look at some code. Can everybody see that okay, size-wise? Okay, I'm going to hook this over here. All right, this is in Scala, but like I said, this works just as well in Java or wherever it implements this. Now, because we're using akka-streams, akka is based on the actor model, and that's like a whole other architectural talk. In fact, Dylan in the audience over here, he gave a talk on the actor model a couple months ago. And really, that's handling how do we handle thread pools and do things in a distributed fashion at the process level. So akka-streams as an implementation sits on top of the actor system, but it abstracts so much of that out that you don't really have to be an expert at the actor system to use akka-streams. So you've got a little bit of decoration here. You got to initialize your actor system and set up a materializer. For the most part, that's all you have to do, so you can kind of move on from there. All right, so here's what we're going to do. the first thing, actually, let me load up. All right. So in this file on the right, we have an iterator that is generating integers. So we're just going to do this first example in memory. So every time I try to get an element from the iterator, it's going to generate a new random integer, and then it'll do that, as long as I like it to. Over here, what we're going to do is we're going to create a source that connects to that iterator. And the source, the type that is going to be emitted out of the source is an integer. So we're going to say source.fromIterator, and we're going to pass in what that iterator is. And then anytime that we invoke demand on the graph, it will pull out records from that iterator in a lazy fashion. So nothing's going to happen until I tell it to. And then at the end of the workflow, we're going to create a sync. And in this particular example, we're going to fold the results. So as elements are coming into the very end, we're going to fold those together. And in this case, we're going to add integers. So we'll always be kind of accumulating the addition of integers. And now all we got to do is build the graph. So we take our source, and we're going to say take 100 elements from this. We're going to filter out even integers. And then, so what we're going to do is we're just essentially count how many even numbers we have in this. That's all we're going to do. So we're going to filter out even numbers, and then we'll just convert those to 1. And by doing that, we will, when we fold that together, we're going to essentially get a count of all the even integers in our list. At this point, all I've done is create an expression tree. Nothing has actually executed yet. So until I tell it to run, it's just going to take up just a very little memory just representing the graph. And then down here, I'm going to say run with that sync, and then that will actually initiate the demand and give it output. So over here, should have had this set up already. So in this case, we got the first 50, 100, or 100, we got 56 even integers. Okay, so pretty simple. Now, what's really nice about the stream library is that we can compose them. So you can build graphs that are composed of multiple graphs from other sources, so they're completely reusable. And since we're building an expression tree that's evaluated lazily, we can easily do that without taking up a lot of overhead. So here you've got different types of composable pieces. You've got a source, which has, it's going to be generating data, so it's got one output. And on the other side, you got a sync that only takes a single input. And then you got all these fancy pieces in the middle where you can create a flow that sits in between a source and a sync. So it's got one in, one out, and then you got kind of different fan-in operations for handling more complex graphs. And so really what you can do is you can build a whole library up of these interchangeable parts, and then you can build a graph and then run it through the graph. And you can do this, and then you can take that graph and fit it into another graph. So you can kind of build these really big applications from these small puzzle pieces. So in this case, on the top left, the composite source, we've taken a source, connected to a flow, connect that to a sync, and then that wraps that whole thing into a brand new source with a single output. And then we can hook that into some other thing. And eventually, we're going to wind up into a sync where it comes into something that has an input, and then that can have its own graph internally. So you can kind of see how we're just building up large workflows from very little pieces. So in this example, what we're going to do is we're going to take our, let me close this. We're going to take that first example and we're going to create a flow out of that middle piece. So we're going to do the same source. We're going to have an iterator that is generating random integers as it's just going to be constantly pushing stuff out. We're going to fold again, But this time what we're going to do is we want to create an actual composable piece that we can reuse in other graphs. So we're going to call this a flow. And if you look at the type signature, it's going to take an integer as the input. That's the first type. And the second type is going to be whatever we expect on the output. So again, we're going to have an integer coming out of this flow. So then we say, okay, create a flow object, filter, and then do the map there. And then that's going to be stored in this even flow variable here. So then down in our graph, we say source, take, and we just say take the data out of here and then run it through the flow now that we've pre-built. You can kind of see how the data types are going to match through the whole thing. So whenever we run this, okay, this time we got 59. And we get an exception because I did something wrong. Okay, I'll have to look. I might not have. Yeah, I think I'm reusing something. So, yeah, but as you can see, like it's the same example. We're just taking that out and building off of it. Any questions so far? Nope. Okay, so something that where akka-streams really shines is its ability to handle asynchrony. So by default, all this is going to happen in a linear manner. But what we really want to be able to do is to parallelize the work, and you can do this a couple different ways. So the first thing you can do is set up asynchronous boundaries in the workflow, and every time you set up a boundary, all of the pieces before that are going to run in its own actor system. And really what that means, if you're not familiar with the actor system, is that's going to run in kind of its own thread pool. So you might be able to say, okay, this particular actor has access to this thread pool of this size, and then so we're going to run this part of the graph in that actor, in that thread pool. And then you could have each piece along the way kind of broken out that way. So if the way you want to distribute this data, you have a real clear, you want things working in different cores or something, you can do that pretty naturally. And all you got to do is say right here .async, and it's going to create a boundary there. And there's a little bit more computation time figuring out, spinning up your actor for that part of the workflow. But once it's all set up, you can just run your data through and leave it on. Another thing you can do is you can tell it to, at particular points in the workflow, say this piece, I want you to run this in across different cores, so you can parallelize it. Let's see. Okay, so before I show you the parallelization, I want to show you a really cool thing about akka-streams. And one of the things you can do is use a built-in DSL language to construct your graph. So in this example, I'm going to kind of build up some interesting objects here. I've got a data type for managing counts. So I'm going to count the number of even and odd values that come into the stream. So I'm going to create a counts type. I'm going to have an even count and an odd count. And then just for scaffolding purposes, I'm going to have an append operator where if I get a new count object, it will increment both of these accordingly. So this is essentially setting up a semaphore. And then we'll go ahead and allow for kind of a base. So now we've got an actual monoid at this point. All right. We're going to create two flows, very similar to what we've seen before. We're going to have an even flow. There's your Pearl Jam reference. So we're going to have, this one's going to count all of our even values, and then we're going to have an odd flow, which is going to essentially count all of the odd values. And so if it's even, we're going to put a 1 in the even slot, and if it's odd, we'll put a 1 in the odd slot. And then we're going to have our iterator function again. We're going to, this time, instead of adding up integers, we're going to fold together the count objects. So this is one of the cool things you can do is and just FP in general. So now we've got a custom type, and we're going to fold this custom type to get something a little more elaborate out of it. So we're going to say, okay, start with the 0 case and the fold, and then we're going to fold each of the either even or odd count types together to get a final one. And here's what we changed. So now, instead of having a linear graph, we're going to have one that is using a DSL, and we're going to fork different paths in the workflow. Now, this is out of the akka-streams library. This part's a little noisy because you got to have some kind of setup code here. So it's kind of, in my opinion, this is kind of gross how you got to do this. You got to call this runnable graph, and then you got to initiate the graph DSL with your sync object. You have to have an implicit builder. This is just kind of the akka-streams Scala library, so you can kind of ignore most of this. But what we're really saying is we're gonna tap into kind of this DSL language here, just in the middle of the code. So what we want to do is we're going to have the source down here. We're going to take 1,000 integers from that source, and now you use this little kind of tadpole operator to go into a broadcasting piece. And what this is going to do is fan out the workflow now. So we had one stream coming in, and now we're going to fan it out into 2 different directions. So the broadcast lets you say, I'm going to have 2 outputs from this broadcast. So all this is really a splitter. So we go, okay, so on the broadcast and the first output, we're going to chain that into the even flow. And then, so that's going to count those up. The broadcast out of the second output is going to go to the odd flow. So we've taken the exact same data, and now we're streaming it to both flows independently of each other. Okay, so that's kind of nice. And then we're going to have a merge piece where we say this one's going to have 2 inputs and 1 output. So we're going to have even flow go into the merge. We'll have odd flow go into the merge. So now both of the inputs are connected. And then we're going to take this merge and say, now funnel that to sync. So we've got the input, we're going to kind of fork it out, do 2 different filters and transformations, and then concatenate those back together. And then we can run that graph down here. So let me go over here. So in that case, it counted 490 evens and 510 odds. Okay. And the graph here supports some pretty sophisticated tools to kind of handle all the fan in, fan out. And what's really nice is that it's self-documenting. So whenever one of the engineers on our team is building their graph, they'll use this DSL, and I can just jump in, and I don't have to care what all the pieces necessarily doing. Just at first glance, I see what the workflow looks like. You know, the data's coming in here, it's going to break out here, and go to these, and then eventually it's going to join in. So that kind of gives me like a very nice holistic view of what's going on without overloading me with a whole lot of, you know, syntax and implementation details. Uh-huh. Uh-huh.
Sometimes transformations are a little bit easier in the front, where you have to do it in the front. You have to split them out, do your thing, and you get to merge them, and you get to split them out for a different reason.
Correct.
So I can see you chaining this over and over again. When you first started showing the screens before, I was thinking that would be a different, I want to say it's a subscriber or producer. I forget what you call it. What is that?
Like a consumer, or yeah. As far as the merge and the syncs. Yeah, so for those, I'll repeat it for the people online. So the question is, because we can have kind of like a graph like this where we have a lot of intermediate pieces, do we find ourselves saying building like composable pieces more often, and then, or do we find ourselves having a bunch of source to syncs and then building those together? Yeah, that's a good question. Really, it just depends on what we're doing. You can do it however you want, really, because you can compose any sets of these things together. So for instance, when I close this particular graph down here, this one is a fully encapsulated graph. That means that the source and the sink are all combined together. So really, I'm just kind of running that graph. But there are ways you can create these graphs where you say, and this is going to emit this output. So, and essentially you're creating like a flow from the graph, and then you can use that for anything else that's, you can essentially use that as your new source for something. So I don't think there's like a real hard, fast rule that we follow. We tend to, I'm going to get in a minute how we use it architecturally, but we work in microservices. And so a lot of times each of our microservices will have like a fairly simple graph, and then we use those process boundaries to say, okay, now we have a new service for this to kind of keep everything simple. And we kind of chain it together that way.
Does that change depending on, from an operations standpoint, as far as monitoring this on runtime, and you're seeing which ones of these either are as a bottleneck, is taking too long, too fast, etc.? Does that change when you start thinking operational-wise? Does that change your design?
That's a good question, and so the question was, does the way we build the graph impact how we can monitor the performance of it? I'm not entirely sure. So I think what the answer to that is that the composition of the graphs shouldn't have an impact on the performance. Like I would expect the runtime characteristics to be the same regardless of how I stitch them together. It's really going to be, okay, well here is something insightful. So there might be parts of the workflow that are costing a lot of, like it's a performance bottleneck. And so one thing you got to figure out is what part of the workflow is doing that. And so there are different ways of kind of trying to profile that, but that does get a little harder. Yeah, so I guess you could say the more you break the graph out and you can run them independently, you could monitor each of those kind of independently. Whereas if you do have everything like a huge single graph and you're trying to monitor the whole thing, that's a little harder. I don't know if that answers your question exactly, but so any other questions about that? No? All right. Let me show you another interesting thing you can do. Okay. In this case, I'm now going to, instead of generating a bunch of integers and reading from that, I'm going to pull in from a file. So totally different data source. And not a whole lot has to change in order for that to happen, but there is kind of a neat thing when reading from files. So I'm going to create a new type at the top called record. And this is just randomly generated, user data. So I've got a username, we got some details and metadata about the user, and then we'll have like this Boolean enabled flag, just true or false. And so I probably should have, okay, so here's what that file looks like. And there's 100,000 records in this file, so more than we want to load into memory. And so what we're going to do is we're going to create a source, and instead of, there we go. And instead of loading it from that iterator, we're going to use the file IO factory. And we say, grab it from this path, so this is a path on my machine to that CSV. And then the cool thing is now you got to describe how do you want to break up the input from that file to process it. So initially when I load a file, it's going to come in as a stream of bytes. But maybe I don't want to handle bytes at that granular of a level. I might want to say, go ahead and read to like a new line character or to some sort of delimiter. So in this particular case, I've chosen a new line character. So you can set your framing attributes and say, okay, use the new line delimiter, create a buffer size of about 256 characters. I can't even remember what that one is. I meant to look that up, but it's true. And then we're gonna encode this using a UTF-8 string. So now what it's going to do is it's going to read through the file, And every time it hits a new line character, it's going to create, that's going to be your element now that's going to go through the stream. So that whole string up to the new line will now go through your stream. But I could have just left it as bytes and sent each byte across as its own element, just whatever I wanted to do. So what we're going to do is map this string. So what we're going to get is each, oh, I shouldn't have done that. Okay, each line in this file, we're going to load that, parse that, and put it into that record type. So we're going to get a string in, we're going to parse it, and then we're going to do some sort of filter on this. So actually, let me do this instead. Okay, so we're going to read from a source, and what this does is going to take that line that I got, and it's going to push it through the record constructor, essentially. And so that's going, the constructor, I have logic down at the bottom that's just going to parse that out and give me a record type. And then I'm going to filter based on the is enabled, and then we'll count the number of records that are enabled. All right? So one thing I wanted to demonstrate in this particular demo was having this operation be expensive. So down in the constructor for the record, I've got, this is a terrible parsing function, but I didn't want to bog it down with like applicatives and stuff. So what I do is I created a slow function in here. It's just something that's computationally expensive. And so we're going to do like a check if a number is prime or not, and we're just going to run that a whole lot of times. It's just totally meaningless, but I just wanted to have some CPU cycles happening. So in other words, I've made the allocation of that record type an expensive operation in the stream now. Okay, so we're going to go source, map it to a record, and then do stuff. So I'm going to have to recompile, actually. Okay, so now we're executing that operation. So that file had, I think it was 100,000 records in it. So it's going to do this ridiculous prime computation for every 100,000 of them. I intentionally made this very slow. So now I've got this kind of awkward moment where I'm going to stare at you guys. What's up? Yeah, how you doing, Lucas? Yeah, it's good. Doing all right, too. Thank you.
Yes. So it's pretty cool. I have to get paired up with what's like. But a couple questions first. What are some, and I realize this is very language specific, or language specific, but what are some of the testing methodologies you use for this? Schema-based testing and inputs? I mean, the first thing I thought of was, yeah, the file was great up until I get a 786,000 line character line.
Yes.
So what are some of the testing strategies you use for this and to protect your sources and things?
Yeah, that's a great question. That's taken us kind of a while to also get the hang of. So that is actually a nice thing about the reactive platform is that part of the paradigm is how do you handle error? And to be able to do it, because whenever you're talking about a data workflow, it's really easy to always consider the happy path, and then when you have something happen that's wrong, you got to make a lot of decisions about, okay, workflows, you like to think about them in a very serial, linear, kind of end-to-end, and when there's an error that happens, and maybe let's say you got a long graph, it could happen on step 5 out of 30, or it might happen at 25 out of 30, and then how do you capture that information kind of in mid-flight? So that is a challenge. And then, there's a couple different things you can do there, and there's a couple different philosophies on the best way to handle that. One way is in your workflow, you would essentially fork for the error case. So just like we were doing with the even and odd, where you said, okay, anything that, split off these values, and then we're going to collect even integers up on this path and odd integers on this path. You can do the same thing for error states. So you could say, okay, this particular map function, this transformation, experienced something that we didn't like, a parsing error or whatever. So we're going to now funnel and capture those on a completely separate branch of the workflow. And then we can audit that. So we're going to log that to our logging provider, or we might be able to do some corrections in code depending on the type of error. Another way you could do it is if you get more functional and you use some of your, you could use like a disjunction where you've got kind of like a right or left error state. And so you could, what that lets you do is kind of have more of a linear flow, and then you just pass the disjunction through the whole way, and then at any point along the way, the disjunction might flip from like a right to a left, meaning that I've had an error, and then it will still propagate through your workflow because of like, monadic law, but it keeps everything very linear still. And then at the point you have the error, you have to provide some context as to kind of what happened at that point. But that is a legitimate challenge. It's not, if you're going from like an imperative way of looking at, program flow, it is a challenge to kind of get to a large graph-based flow and then kind of capture and handle error. You got to think about it a little differently. Does that answer your question? Okay. Yeah.
Unexpected error standpoint, you can say, well, restart this particular part of your flow and clear out your state or whatever it is that you want to do. I guess functional programming. But yeah, it can like go and try to self-heal itself with the standard actor-based method of doing that.
So as we saw, this operation took 58 roughly seconds. So the cool thing is now we might say, well, we've got a lot of cores on this machine. I'd like to utilize some of those cores to handle this process. So all I've got to do is say map, but instead of the standard map, I say map async, and I can provide the number of cores as my max, and you can dynamically specify this based on the machine you're running on. I just stuck a static in. And then it's the same thing. The only difference is that instead of this returns a future now, so an asynchronous execution essentially, but it's going to accomplish the same thing. So when I run this, we'll still have a slightly awkward wait time, but it will be a little less awkward because it'll happen faster, hopefully. Or it'll run longer and ruin my demo, and that's really embarrassing. Yes. There we go. So about 16.8, not too bad. Okay. So all I had to do is a keyword change. It's all built into the framework, so it handles asynchrony very well. And I could easily, apply this in the different places that strategically it makes more sense to run that way. Any questions about that? Yeah, pretty simple. Okay, real quick, we're going to shift gears. So at Augsburg, we use this a lot. And here's kind of an example architecture that we use. So we use Kafka for our message brokering. That works really well. So I don't know how many of you are familiar with Kafka? Nope, few, okay. So essentially, what about a message brokering system? Anybody, like what's the Microsoft one? BizTalk, some others, okay. So Kafka essentially is a way of handling communication between processes in a distributed manner. And I'm not going to get into all of that paradigm, but what we do instead of having like RESTful services, we use just kind of a standalone service that listens to Kafka, and Kafka is kind of our messaging conduit between all of our services. And so each service, each microservice, essentially is an akka-streams workflow. And so we try to keep those services pretty small, and each of them has a singular graph to accomplish its work. So it's going to act as an input and output. And really what we're trying to do is we're trying to model a lot of even functional concepts with pure functions at the service level. So essentially each of these are kind of these immutable input to output sort of style. And so then we kind of build on from there. So you might have Kafka stringing together a bunch of them in our architecture that allows for different channeling and paths that the data can take. And it can loop back in the earlier stages if need be. So we get a lot of composable reuse out of these. And it also just keeps it very simple. So each service is using one of these streams, and it's very predictable what you're going to see in that service, and it's very easy to read it for the most part. And also, there are a lot of enterprise integrations. So if you're working with kind of more enterprisey systems, there are a lot of pre-built akka-streams implementations and integrations that it can hook into. So for instance, there's the Alpaca project, which I'll bring up their GitHub page. And this provides, that's exactly what it is a bunch of pre-made integrations. So you can kind of look through the list here, but you got Cassandra, CSV readers, Elasticsearch, you got all the, Mongo, so Hadoop, that kind of stuff, SQS for Amazon, you got Slick database work. So there's all kinds of ways that you can tap into these things as a potential source, and so you really don't have to write a lot of code to pull it in. And of course, there's a Kafka one called Reactive Kafka that we use that's essentially opens up an always-on pipe, and then as fast as messages fly in, we can in live, transform that kind of across our pipeline. And that's it. So any final questions? Yes. Do we run into problems with sources that aren't back pressure aware? That's a good question. The way that the API works, whenever you have a source, if you're using the akka-streams framework, that's going to kind of force it to handle back pressure. And then you have certain areas where you can say, here's what happens if the back pressure fails. So essentially, like if you've got something that you issue demand upstream, and no matter what, it's going to give you just a whole bunch of stuff, you kind of give it these overflow strategies. And you have to pick at that point, are you going to just drop the records? Are you going to fail the stream? And there's like a handful of different things you can do to operate with that. Now, we haven't run into that particular scenario, just the way we've built the architecture, but it is a potential risk you run. So you can't just be completely unaware of what you're connecting to. Mm-hmm. Scott?
What about the reverse problem? Like this whole model is about sources that are giving you a lot of data. What about sources that will start you? Can you use it in the same system?
You can. So essentially, by default, if you've got like a slow producer and a fast consumer, what'll happen is that the consumer will signal demand upstream, and if it can't issue demand, then it just waits. And then you could have it to where, if it's important for your workflow to time that out or to signal that as like, hey, it's been so long, so like stop the process if it's been so many milliseconds before I've reached something, you can do that. Or you can just leave it always on. So for instance, in our architecture that we have, since we have like Kafka, we've got our services are always listening to Kafka topics, that queue. And so there might be stages where nothing's happening in the pipeline, and they're just waiting. And the graph has demand on it, and then the second that something shows up in the Kafka topic, it can suck it in and process it. But otherwise, it just sits there kind of idle. But we could say, all right, it's been about a minute now. Let's go ahead and shut it down, and then we'll restart later to listen again. Yes. And that's one thing that we're doing is, we Dockerize everything, and on AWS, you can just say, oh, I got a lot of demand, so fire up more things to consume from those topics in parallel, and then spin them down whenever, the demand reduces.
So how do you decide what's the scaling points? If it's, so the system can inspect its own, it can inspect its own stream, stream use, or how, do you have some separated system that's looking at to see how much resources it's using, and that's what's causing the scaling? Or does the system itself, like, does your streaming system also, is it also able to look at, like, how much data is going through the stream and scale?
You can do that different ways. So when you're using, for instance, like a message queuing system, you can, so by default, you can look at like your CPU load or your memory pressure and just say, oh, okay, this particular, this particular container is consuming a lot of CPU, so that can be your rubric for expanding outward. You could also look at the actual, like in Kafka's case, you can look at the amount of work you have queued up in Kafka, and then you could scale it based on that as well. So you got, a couple different options. Sure.
Okay, so you guys have a lot of messages flying around. Scala is a very strongly typed language.
Mm-hmm.
Do you find it good to keep the messages lightly typed, just, like a general structure, or do you guys try and add significant amount of typing?
Good question. We love typing, but for a lot of our services, we might have a payload that comes across where we only care about certain attributes of that payload, but not the whole payload. So we made a decision to use JSON as our message format. There's a lot of others out there that have different benefits and pros and cons. We chose JSON, and so typically what we'll do is when a service gets the JSON in, we will have it typed to say, okay, here's the message, here are the attributes we care about, and then the rest can be like a JSON blob, essentially. But we type where, anytime you need to touch anything in there, we try to type that. Any other questions? All right, well, thank you guys. Just real quick, we will have one more talk next month, and then we'll be off in December for the Christmas holiday. And then I don't have a whole lot of other talks queued up for the new year, so if you guys would, anybody would like to give a talk or knows anybody, if you're sick of hearing about Scala and want to see a different language, then we would love a variety and mix. So please just contact me afterwards. But thanks for coming, guys.